Hello everyone. Today I'm going to walk you through the design, implementation, and deployment of the state of the art time series anomaly detector in critical industries such as aerospace, infrastructure, and financial systems. Equipment is monitored continuously by dozens of sensors. The dataset we are using today is a NASA Soil Moisture Active Passive, which records spacecraft power usage and module command signals across 25 parallel channels. Our core challenge here is what that we are operating in an unsupervised machine learning setting. In real world monitoring, anomalies are rare, highly unpredictable, and almost never labeled. This means we cannot train a standard classifier to detect issues. Instead, our goal is to build a model that learns the underlying normal operational pattern of the spacecraft with such high precision that any abnormal event will cause a visible mathematical deviation. To solve this, we built a temporal convolutional network or TCN autoencoder. The system takes multidimensional sliding windows of normal sensor data, compresses them into a lower dimensional bottleneck representation, and then reconstructs them. In the following minutes, we will explore why TCNs are superior to recurrent networks for sequence modeling, how we applied extreme value theory for robust anomaly thresholding, and finally, we will explore the interactive Streamlit dashboard design to help operators analyze detected events. When working with sequence data, recurrent neural networks like LSTMs have historically been the default choice. However, LSTMs suffer from two major flaws: sequential training bottlenecks and unstable gradient flows, because an LSTM must compute the hidden state at a timestamp t t minus 1 before it can compute the state at timestamp t. It cannot process sequences in parallel. This severely limits the training speed. Temporal convolutional network solves this by framing sequence analysis as a 1D spatial operation. In a TCN, we apply one-dimensional convolutional filters across the sequence. Since the weights are shared, we can compute representations for all time steps in parallel. In our project, training a three-layer TCN autoencoder on CPU over 2766 windows took only like 26 seconds. An equivalent LSTM would take minutes to train. An equivalent LSTM would take minutes to train on the same hardware. Furthermore, TCN manages gradients much better in long sequences. LSTMs propagate errors through long backpropagation through time chains, which often leads to vanishing or exploding gradients. TCNs are residual skip connections, adding the input of the residual block directly to its output. This creates a direct path of gradients to flow backwards, allowing us to train deeper models stably. Finally, TCNs give us exact control over sequence memories by adjusting the kernel size and dilation factors. We can mathematically define the exact res- receptive field configurations. The receptive field is precisely 15 time steps. The next step would be anomaly scoring and extreme value theory. Once a model is trained, we pass the test telemetry data through it to obtain the reconstructions. For each time step, we calculate the reconstruction error using the mean squared error because the autoencoder was trained only on a normal patterns. It reconstructs normal telemetry with a very low error. However, when it comes and However, when it encounters an anomalous sequence, it struggles to reconstruct it, resulting in an error spike. To prevent false alarms caused by temporary noise, we apply an exponential moving average, smoother with the span of 10 to our raw signal. Once we have the smoother error, we must establish a threshold to flag anomalies. A simple approach is percentile thresholding, where we take a fixed quantile like the 99th percentile of normal errors and flag everything above it. While while easy, this method is static and does not adapt well to heavy tail distributions. To overcome this, we implemented a peak over threshold or POT, which is based on extreme value theory. Instead of looking at the entire error distribution, POT models only the extreme tail. We choose an initial higher quantile, like the 95th percentile, to define what is extreme. We then collect all the excess above this threshold and fit a generalized Pareto distribution to them using a sci-fi using cumulative probability function of this fitted distribution. We calculate a final anomaly threshold based on a target probability of exceedance. This gives us a mathematical rigorous and adapted threshold that accounts for static shape of extreme errors. Now let's look at the pipeline implementation. Our project is fully containerized using Docker and Docker Compose, ensuring that the entire environment is reproducible on any machine with a single command. The pipeline brings us to the pre-processing data. The script is designed to download the telemetry zip files from AWS S3, extract files for channel P1 and fit them in max scaler if the external S3 server is offline. The script automatically triggers a high quality synthetic generator. And next, train.python. This file loads the processes the training data into training data. It instantiates the TCN autoencoder class in PyTorch, which is constructed dynamically based on the layers and kernels as defined in the submission.json. In evaluate.py, loads the saved weights, reconstructs the text data, applies the EMEA smoothing, fits the GPD for the POT threshold, and writes three CSV result files. Now let's explore the interactive Streamlit dashboard. At the top of the page, the operator is graded to a clean dark themed interface showing the four primary metric cards, total timestamps, the number of channels, the active anomalies, and the anomaly ratio. This gives an operator an immediate snapshot of the health of the spacecraft telemetry stream. The first interactive section is the multi-channel signal explorer. By using the multi-select drop-down operators, you can choose any subset of the 25 telemetry channels to display on a synchronized interactive timeline. This helps visualize the correlation between different space modules. Right below is the reconstruction chart. For example, you can overlay chart. Here we can select one specific channel, for instance, channel 0, which represents the main telemetry signal. The chart plots the original signal in a solid blue and TCN reconstruction in a dotted red, uh, in a dashed red. As you can see, that during a normal operational phases, the red dashed line tracks the blue line almost perfect. However, during anomalous phases, the reconstruction fails and dashed line diverges. Next is the anomaly score timeline. This chart plots the raw reconstruction error in gray and the EMA smoothing anomaly score in green. A red horizontal line displays our threshold. In the side in the sidebar, operators can select a threshold references, either like 0.0442 or percentile of 0. Or use the manual slider to dynamically change.